Transmission outage scheduling optimization. Final demo. Objective motivation. Power grids face variable utilizations and require routine maintenance to ensure reliability and safety. Our objective is to develop an optimized and safe maintenance scheduling strategy for transmission outages. Under the guidance of Caper, Dr. Raza, Dr. Hadidi, and Dr. Clark, we are building a framework for transmission outage scheduling optimization. Our key goals include prioritizing outages using optimization techniques, designing a MATLAB GUI for data navigation and simulation visualization, enabling automated analysis and an accurate low-impact evaluation. Project goals and deliverables: reduce runtime, extend stimulation time frame, enhance GUI function, stabilize parallel processing, refine data time, data handling, resolve loop execution errors, enhance hardware reliability, and streamline data processing in our total output. Our block diagram. This block diagram outlines the architecture of our transmission outage scheduling framework. We will begin with this existing code and we integrate it into MATLAB to serve as our foundation. From there, we utilize MATLAB for running our transmission simulations. Using MATLAB App Designer, we also build a custom GUI. We pull outage data and run it through the GUI to populate a dashboard where we can visualize and see all the scenarios in real time. Ultimately, this setup allows us to stream the process from raw data to simulate, enabling efficient analysis.
So since our project was mainly software-based, we don't have a lot of hardware requirements. There's no special equipment or any offsite or cloud resourcing at all for our project. The baseline, or the median type of system we needed was an Intel processor, either i5 or i7, with a 32 gigabyte system of RAM. This was the middle of the road system that we ran our program on. We had a few members with either higher or lower grade settings than this, and they were still able to run the system as well. So our software design requirements were MapPower was the main external tool we used. And we used a lot of MATLAB add-ins, such as the curve fitting toolbox, the global optimization toolbox, and optimization toolbox, parallel computing, and the widgets toolbox as well.
Our software design is kind of based on this flow chart. You kind of read in our test file v10, which is the base case or the base code for MATLAB. Read that in. It reads in data, which is processed by MATLAB. From there, you can open the GUI. The user will be able to select a start date and end date, as well as any amount of 25 outages. From there, the GUI will filter all that data, giving you a successful filtering prompt, alerting you, telling you to go to the next tab in the GUI, the optimization tab. Once you hit that button, particle swarm, which is our main technique for scheduling, will run in the background, which will then display each outage selected, giving it a start time as well as an end time based on how long the outage is supposed to last, giving you a optimized scheduling for any and every outage that you have selected.
So here's our GUI where you can select up to 25 outages, and it displays the outage number, bus to and from, the branch number, and any special conditions that is associated with that outage. You can also pick the start date and the end date, and you can filter the parameters to filter the baseline file to only display the dates you showed and what buses are affected on those dates. And after you filter, it takes a little bit of time, but a pop-up will tell you when all the data has been extracted, and you can move on to the next tab. And here's the next tab where you can hit optimize, and it runs the optimize file to show you the specific date that the outage will start. It'll show you the outage number, the start date, and the end date, and the total duration of days that it'll take to do that outage. If an outage can be completed in the date range you selected, it will not show up on this page.
So for methodology, the theoretical approach behind the optimization is that we apply particle swarm optimization, PSO, for scheduling prioritization. We found this as part of our literature review back near the beginning of the semester as a fast and effective method for complex outage optimization. One of the benefits is it was easy to implement a N-1 contingency analysis to ensure that we can maintain system reliability. Even if a single bus or branch fails, we're able to check and make sure that the rest of the system is intact.
Our computational models is obviously built upon MapPower, an external tool. This is a toolbox that you can download, and it gives you power system simulation code, and it accurately models power flow and system behavior for, in our case, an 118 bus system. We also implemented a built-in MATLAB toolbox, the parallel computing toolbox, which allowed for asynchronous parallel processing and parallel processing, just to reduce the runtime and enhance scalability, because you're testing for all the branches and all the buses. So this just reduces the amount of time necessary to process those simulations.
And for experimental design, we created a GUI to control the simulation and to visualize the data for the user. And the data we're visualizing is the outage selection, the map generation, and the load tracking. To test this, we use the Caper provided data sets, which include the initial grid configuration, the outage data, and the hourly load profiles across an entire year. And we employ block dispatching and extended time simulation of over 30 days to simulate realistic maintenance planning scenarios.
Discussing our results, we do have improved runtime. Previous semesters, code took a fairly long time to run, around 20 minutes just to process 2 days. We've been able to simulate an entire year with every outage in about 15 minutes, depending on the hardware being used. As I said before, parallel processing was used, and this has led to significant reduction in simulation times, and we're able to handle these large data sets, these long and big simulations, within a reasonable amount of time, I believe. And with enhanced outage prioritization, as mentioned before, we've integrated particle swarm optimization, which is meant to improve the accuracy and quality of outage scheduling. We validated this through a literature review, and we deemed it the top performing method for complex optimization in a power system.
Also, we did manage to develop a functional GUI prototype and have that up running and operational. We were able to successfully extend the simulation past the previous 30-day limit. As discussed previously, we're able to run an entire year with N-1 contingency in place as well. As part of the GUI, we are able to show a interactive selection of outages, date ranges, and system components through the outage selector, data tabs, and the outage map visualization can enable users to monitor and manage simulation parameters as well.
Some of the challenges we've had developing our project were inconsistent outcomes from the parallel processing and us having unpredictable results because of that. We also had data formatting issues with the datetime file and some of the other files we were provided with. Had some execution errors within our par4 loops, impacting the processing reliability of our parallel processing. A lot of hardware-related issues like instability that were affecting our performance and consistency with our system, and complex manipulation requirements for our total output CSV file, making data integration difficult.
Future directions for this project, we did use a real-world system, and we tested real-world data in our simulation. This has the capability of supporting larger scale systems or other regions. The optimization algorithm enhancement, we've explored a hybrid approach in particle swarm optimization just to improve the accuracy, the convergence speed, and adaptability of these complex outage scenarios, because you can select any number at any given time. GUI improvements. You can enhance the MATLAB GUI with a bit more interactive components, a faster real-time simulation update, and features like scenario comparison and dynamic data upload, just to improve user experience and accessibility to our project.
So in conclusion, this project has successfully demonstrated our approach to optimizing transmission outage scheduling using particle swarm, as well as parallelism, and uses a MATLAB-based GUI for a more integrated and user-friendly experience. Through integrating automatic contingency analysis and load impact, the system lets operators make well-informed and data-driven decisions when trying to schedule a prioritized outage. The core of this optimization, as mentioned, is particle swarm, which identifies and shows the optimal scheduling outcomes, balancing system reliability with operational constraints. And we've used parallel processing to significantly reduce the amount of time it takes. This is especially useful for large-scale power systems with numerous variables, and has the benefit of being scalable, whether you're talking about large-scale or sample size power systems. The MATLAB GUI that was developed in this project serves as a very powerful interactive platform for both data navigation and simulation control. It simplifies a lot of the end user process while providing a clear visualization, control options, and a seamless integration with the back-end algorithms and processes, making the tool both robust and accessible. Ultimately, this project really bridges the sort of theoretical optimization techniques that we spent some time researching and the real-world application of how do we make it work. We've delivered a scalable, intelligent, and resilient tool for transmission outage planning, supporting informed, data-driven decisions and improving system reliability.
With that, here are our references, and that concludes our technical video presentation.